Namaskar, I am Dan Gaude, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the examples of Eulerian angle. Now see here example, if the matrix of transformation from space set of axis to body set of axis is equivalent to a rotation through an angle xi about some axis through the origin, then show that cos of chi by 2 is equal to cos of phi plus psi divided by 2 cos of theta by 2. Solution: we know the matrix of complete rotation from space set of the axis to body set of axis in terms of Eulerian angle phi theta psi are given by A is equal to cos psi cos phi minus cos theta sin psi sin phi cos psi sin phi plus sin psi cos theta cos phi sin psi sin theta minus sin psi cos phi minus cos theta cos phi sin phi minus sin phi cos sin psi sin phi plus cos theta cos psi cos phi psi sin theta sin phi minus sin theta cos theta. It is given that this matrix of the rotation is equivalent to the matrix of the rotations of coordinate axis through an angle chi about some axis with the same origin. Equivalently, it means that it is always possible by means of some similar transformation to transform the matrix A to the matrix B obtained by rotating the coordinate axis through the angles chi about some axis with the same origin. This matrix of rotation is given by the either B is equal to cos psi sin psi 0 minus cos sin psi cos psi 0 0 0 1 or B is equal to 1 0 0 0 cos psi sin psi 0 minus sin psi cos psi. Call equation number 2. It is well known that under similar transformation, trace of the matrix is invariant. Using this result, we have trace of A is equal to trace of B. Cos psi cos phi minus cos theta sin psi sin phi plus cos psi cos phi cos psi cos theta minus sin psi sin phi plus cos theta is equal to 2 cos psi plus 1. 2 cos psi plus 1 is equal to cos psi cos minus sin psi sin phi plus cos theta into cos psi cos phi minus sin psi sin phi plus cos theta is equal to 1 plus cos theta cos of psi plus theta phi plus cos theta. 2 cos psi plus 1 is equal to 2 cos square of theta by 2 into 2 cos square of 3 psi plus 3 phi divided by 2 minus 1 plus cos square of theta by 2 minus sin square of theta by 2. 2 cos psi plus 1 is equal to 4 cos square of theta by 2 cos square of phi plus psi divided by 2 minus 1. 2 cos psi plus 1 is equal to 4 cos square of theta by 2 cos square of I plus psi divided by 2. Cos square of psi by 2 is equal to cos square of theta by 2. Cos square of phi plus psi divided by 2. Cos of psi by chi by 2 is equal to cos of theta by 2 into cos of phi plus psi divided by 2. Next, moment of inertia and product of inertia. Definition of moment of inertia: uniformly rotating body possesses the tendency to oppose any change in its state of rotation motion. This quantity is called the moment of inertia. Theorem: obtain the angular momentum of the rigid body about a fixed point of the body when the body rotates instantaneously with angular velocity omega in terms of the inertia tensors. Proof: consider a rigid body composed of ion particle having masses mi and position vector ri with respect to the fixed point of the body. Since the translational motion is absent and the body rotates about an axis passing through the fixed point, let omega be the instantaneous angular velocity of the particle body. If vi is the linear velocity of the ith particle, then we know that it is given by vi is equal to w cross ri. If L is the total angular momentum, then it is equal to the sum of the angular momenta of an individual particle. Therefore, we have L is equal to summation of I is equal to summation of Ri multiply Mi Vi. L is equal to summation of Ri multiply Mi into W cross Ri. L is equal to Mi into Ri cross W cross Ri. Using the vector quantity A bar cross B bar cross C bar is equal to A bar dot C bar B bar minus A bar dot B bar C bar. We obtain L is equal to summation of Mi Ri square W minus summation of Mi Ri W Ri. Let the component of the position vector Ri, the angular velocity omega and the angular momentum vector L be denoted by Ri is equal to Ixi plus Yji plus Kzi. W is equal to Iwx plus Jwi plus Kwz. L is equal to Ilx plus Ijly plus Klz. Using equation 3, we write Ilx plus Jly plus Klz is equal to summation of Mi Iwx plus Jwi plus Kwz into Ri square minus Xiwx plus Yiwi plus Ziwz into Ixi plus Zwi plus Kzi. Ilx plus Jwi plus Kwlz is equal to Iwx Mi rj square minus xi square minus wy mi xi yi minus wz mi xi zi plus j minus wx mi xi yi plus wy mi ri square minus y square minus wy mi yi zi plus k minus wz mi xi zx, and we get ly is equal to minus wx mi xi yi plus wy mi ri square minus y square minus wz mi yi zi lz is equal to minus wx mi xi zi minus wy mi yi zi plus wy mi ri square minus zi square. We write the component of the angular momentum as Lx is equal to Ixx Wx plus Ixy Wy plus Ixz Wz. Ly is equal to Iyx Wx plus Iyy Wy plus Iyz Wz, and so on, where the coefficient of Wx, Wy, Wz are respectively defined by Ixx is equal to mi ri square minus xi square is equal to summation of mi y square plus z square. Ly is equal to mi ri square minus y square is equal to summation of mi xi square plus z square. Izz is equal to mi ri square minus z square is equal to mi square xi square plus y square, and are called the moment of inertia about x, y and z axis respectively. Equation 6 shows that the moment of inertia is the sum over the particle in the system of product of masses and the square of its perpendicular distance from the axis of rotations. Also, the quantities Ixy, Ixz, Iyz are called the product of inertia and is defined by Ixy is equal to Ixz is equal to Iyz is equal to, therefore Lx, Ly, Lz is equal to Ixx, Ixy, Xz and multiply Wx, Wy, Wz. Therefore L is equal to I multiply W, where I bar is called the moment of inertia tensor or inertia tensor, and gives it is always possible to find a set of axes with respect to which all the products of inertia tensor vanish, leaving off diagonal terms, and the axis is called the principal axis of the body. Take care of